Good morning. Today we will study about the structure of AB type ionic solids. In AB type, three structures: sodium chloride, zinc blende, and cesium chloride will be discussed one by one. First, we will discuss about the structure of NaCl. In first step, from size of Na plus ion and chloride ion, radius ratio is calculated and coordination number is predicted. Size of Na plus ions is 95 picometer and size of chloride ion is 181 picometer. Then radius ratio, that is radius of cation divided by radius of anion, and it is 0.52. The value of radius ratio lies within the limiting value, that is 0.414 to 0.732. Hence, we can say that the coordination number is 6. As each sodium ion is surrounded by 6 chloride ion and each chloride ion is surrounded by 6 sodium ions. And sodium ion is represented by a dark circle and the chloride ions by the hollow circles. As the size of chloride ion is large, it has CCP types arrangement. That is, chloride ions are at the corners and in the center of each face. That is, chloride ions are at the corners and in the center of each face, and sodium ions are at the octahedral sides, as we have already studied about the octahedral sides and the tetrahedral sides. So sodium ions, they occupy all the octahedral sides. As there is only octahedral sides for each ion in CCP arrangement, there is only one octahedral side for each ion in CCP arrangement. Therefore, the stoichiometry is 1:1. For closed-pack structure, the value of radius ratio should be 0.414, but actually it is 0.52, as we have seen from the radius ratio, that is the value of radius ratio is 0.52 in case of NaCl, and for the CCP type of the structure it should be 0.414. So we can say that is, to accommodate large sodium ions, the arrangement of chloride ions open up. So chloride ions have CCP type of the arrangement, and from the structure, in a unit cell, 4 sodium ions and 4 chloride ions are present. It indicates that the stoichiometry is 1:1. In structure, chloride ions are at the corners and at the center of each face. So the number of chloride ions we can calculate, that is 8 multiplied by 1/8 plus 6 multiplied by 1/2, that is 1 plus 3 is equal to 4. Because the sharing of chloride sharing at the corner is 1/8 and there are total of 8 corners, so we multiplied it 8 multiplied by 1/8 plus 6 on in the center, so they are divided by 2 and we get 1 plus 3 is equal to 4, and 12 Na plus ions are at the edges and 1 at the center. So the number of sodium ions 12 multiplied by 1/4, because each is shared by 4 cube plus 1 which is in the center, so total sodium ions are 3 plus 1, that is 4. Hence, for each sodium ion there is 1 chloride ion. It also comes from the stoichiometry is 1:1. as we have seen in the structure of NaCl. And Na plus ion is octahedrally surrounded by 6 chloride ions as shown, and here we have shown that chloride ion is octahedrally surrounded by 6 sodium ions. So this is the structure of NaCl. Similarly, we can discuss about the structure of cesium chloride. Structure of cesium chloride, as the size of cesium chloride, cesium ions, and the size is 168 picometer, and the chloride ions, the size is 181 picometer, and radius ratio is, that is radius of cation divided by radius of anion, it is 0.93, and this value is more than the 0.732. Hence the structure opens up to accommodate cesium ions because the value is more than 0.732. Hence we can say that the structure opens up to accommodate cesium ions. This is the structure of cesium chloride, and in this cesium ion is surrounded by 8 chloride ions, and each chloride ion is surrounded by 8 cesium ions. Because the radius ratio is more than 0.73, so we can say that is cesium ion is surrounded by 8 chloride ion, and each chloride ion is surrounded by 8 cesium ions. And in this arrangement, the chloride ions are present at the corners of the cube, and chloride ions which are represented by the hollow circle, while cesium ion occupy the body center of the cube and represented by the dark circle. And from this structure we can say that there are 8 chloride ions at the corners. So the number of chloride ions in a unit cell is 8 multiplied by 1 by 8, that is total 1 ion, and cesium ion is at the center of each unit cell, so the number of cesium ion is 1. Hence the stoichiometry is 1:1. By knowing the stoichiometry of cesium and chloride ions, we can say that a unit cell of cesium chloride is made up of one molecule of cesium chloride, that is Z is equal to 1. Cesium ion is surrounded by 8 chloride ion, and it is shown in the structure A, and structure A is a unit cell of a structure B, and in structure B we have shown whole of the unit cell, and in structure A we have seen that its cesium ion which is present in the body center, it is surrounded by 8 chloride ion, and each chloride, as it has shown in structure B, that each chloride ion is surrounded by 8 cesium ions. So the stoichiometry is 1:1. Another example of this type is cesium bromide, cesium iodide, thallium chloride, thallium bromide, etc. Then we study about the structure of zinc sulfide. This is also known as zinc blended structure, and in this the radius ratio is calculated, that is size of zinc ions divided by size of the sulfide ions, and radius ratio is found to be 0.4, and the coordination number from radius ratio value is 4, and the value of radius ratio, that is 0.4, is more than the lower limiting value, that is 0.225. In this structure opens up, so sulfide ion have CCP type of the arrangement. and sulfide ion represented by hollow circles. As in this structure, sulfide ions, they are represented by the hollow circles. They are at the corners. Sulfide ions, they are represented by hollow circles. They are at the corners and at the center of each face of a cube. That is, it has CCP type of the arrangement. Sulfide ions has CCP type of the arrangement because they are present at the corners and at the center of each face of the cube. And zinc ions represented by the dark circles. They occupy half of the tetrahedral sides. That is because the stoichiometry is 1:1, so all the tetrahedral sides are not occupied, only half of the tetrahedral sides they are occupied. And each zinc ion is surrounded by 4 sulfide ions as shown in this structure. That is, each zinc ion, it is surrounded by 4 sulfide ions, and each sulfide ion are at the corner of a regular tetrahedra. Sulfide ions, they are present at the corners of a regular tetrahedra. Because there are 8 corners, so total sulfide ions are 8 multiplied by 1 by 8, that is 1, total 1 sulfide ion. And these zinc ions, they occupy half of the tetrahedral sides. So the stoichiometry is 1:1. By knowing this stoichiometry, we can say that a unit cell of zinc sulfide is actually made up of 4 molecules of zinc sulfide. Complete, that is, one unit cell of zinc sulfide, it is actually made up of 4 molecules of zinc sulfide. And other examples of a zinc blend structure is CuCl, CuBr, CuI, etc. Then we will study about the structure of type AB2 type, that is, in which the stoichiometry is 1:2. And in this category, fluoride structure will be discussed. And structure of a fluoride, that is calcium fluoride, from the structure which is given below, we can say that calcium ions are at the corners and at the center of each face. And that is calcium ions, which is shown by the dark circle. They are present at the corners and in the center of each face. That is, calcium ion have CCP type of the arrangement in a cube, and fluoride ions, they are at the center of each unit cell. Fluoride ions are present at the center of each unit cell. That is, it occupies all the tetrahedral sides. In zinc blend structure, half of the tetrahedral sides were occupied, but in calcium fluoride structure, because this stoichiometry is 1:2, so all the tetrahedral sides are occupied. And each calcium ions, for each calcium ions, there are 2 tetrahedral sides, and all the tetrahedral sides are occupied by fluoride ions. So the stoichiometry of the compound is 1:2. From this structure given below, we can say that each calcium ion is in contact with 8 fluoride ions. Each calcium ion is in contact with 8 fluoride ions, and each fluoride ion is in contact with 4 calcium ions. So the coordination number of calcium ions and the fluoride ion is 8 and 4 respectively. In a unit cell, from the figure as shown, we can say that the number of calcium ions, total number of calcium ions, 8 multiplied by 1 by 8 plus 6 multiplied by 1 by 2, that is 3 plus 1, because all calcium ions are present at the corners and in the face centers. So there are total of 4 calcium ions, and number of fluoride ions, because all the tetrahedral sites are occupied, so total number of tetrahedral sites are 8. So there are total of 8 fluoride ions. From this stoichiometry calculation, it is clear that a unit cell of calcium fluoride is made up of 4 molecules of calcium fluoride. And other example of this type of structure is barium fluoride, strontium fluoride, etc. And this is all about this ionic structure of type AB and AB2 type. And the points to remember in this is that a particle at a corner of a unit cell is shared between 8 unit cells, hence its contribution is 1 by 8. And a particle at a face center of a unit cell is shared between 2 unit cells. At the face center, it is shared between 2 unit cells, so its contribution is 1 by 2. Then we will study about the radius ratio effect and the coordination number. Ionic compounds have generally definite shape in which each ion, whether it is cation or anion, is surrounded by a fixed number of oppositively charged ions, that is termed as coordination number. However, as the coordination number depends on the relative size of cation and anion, that is, for example, we can say in an ionic compound of the type AB, the coordination number of A plus and B minus n must be same. Similarly, in an ionic compound of AB2 type, the coordination number of A plus ion is double than the B minus n. The most stable structure which can be predicted on the basis of coordination number, which is determined by the radius ratio. So what is the radius ratio? It is defined as the ratio of radius of cation to radius of anion. And the utility of radius ratio is that it helps in predicting the structure of ionic solids, that is most stable arrangement of ions. And cations and anion in an ionic solid arrange in such a way to attain stable structure. They are arranged in such a way to attain stable structure when the attractive forces between the oppositively charged ions are maximum and repulsive forces are minimum. For example, in a crystal structure, A plus ion surrounded octahedrally 6 B minus ions, that is coordination number of A plus is 6, in which 4 B minus ions are in one plane and 2 ions are placed one above the plane and one below the plane, in such a way that is anions are touching each other. When the size of anion is small and the size of cation is large, when the size of anion is smaller and the size of anion is larger, then the coordination number decrease. And when the size of anion is large and the size of cation is small, then the coordination number decrease. That is, when r plus is greater than r minus, the radius ratio value, that is r plus divided by r minus, increase, and that is structure become unstable and the coordination number increases. And there are two ways to increase the radius ratio, that is, we can increase the radius ratio either by increase in size of the cation or by decreasing the size of anion. And the same effect is also observed when pressure is increased. That is, when pressure increases, the number of nearest neighbors also increases. When size of a cation is smaller as compared to anion, the radius ratio value decreases and the structure again becomes unstable and the coordination number decreases. And there are two ways to decrease the radius ratio, either by decreasing the size of cation or by increasing the size of anion. And same effect is observed when temperature is increased. That is, when temperature increases, the number of nearest neighbor decreases. And from this we can conclude that there are certain limiting values of radius ratio in which the coordination number is 6, that is in the range between 0.414 to 0.732. The coordination number is 6, and limiting radius ratio, if the limiting radius ratio is 1.0, then the coordination number is 12 and the structure will be close packing. And if the limiting radius ratio is 0.732 1.0, then the coordination number will be 8 and the structure will be cubic, and example is cesium chloride. And if the limiting radius ratio is in the range of 0.414 to 0.732, then the coordination number will be 6 and the structure will be octahedral, and example is NaCl. And when the limiting radius ratio is 0.225 to 0.415, then the coordination number will be 4 and the structure will be tetrahedral, and example is zinc sulfide. And the limiting radius ratio is 0.155 to 0.225, then coordination number is 3 and it will be triangular, example is B2O3. And limiting radius ratio, if is less than 0.155, then coordination number will be 2 and the structure will be linear. And for example, you can say if the radius ratio value is in between 0.414 to 0.732, the coordination number is 6 and it gives rise to a stable structure. If the radius ratio value is less than lower limiting value, the coordination number changes from 6 to 4, and when the value is more than upper limiting value, then the coordination number changes from 6 to 8. If the value is lower than 0.414, then the coordination number changes from 6 to 4, and if the value crosses the 0.732, then the coordination number changes from 6 to 8. And thus radius ratio value helps in predicting the most stable arrangement of ions in an ionic solid. And application of radius ratio helps in finding out the structure of ionic solids, that is structure of NaCl. We can calculate the radius ratio and it comes out to be 0.52. In case of NaCl, the radius of sodium ions divided by radius of chloride ions. Radius of sodium ion is 95 and radius of chloride ion is 181. Then radius ratio comes out to be 0.52, and the value is in the limiting region of 0.414 to 0.732, hence coordination number is 6. So sodium ions occupy octahedral holes while chloride ions form CCP arrangement. Similarly, the structure of zinc sulfide, in this the radius ratio comes out to be 0.40. So we can say that the value of radius ratio lie within the limiting value of 0.225 to 0.414, hence the coordination number is 4 in case of zinc sulfide. That is, zinc ions occupy tetrahedral holes and sulfide ion they form the CCP arrangement. Similarly, the structure of rubidium iodide, the radius ratio comes out to be 0.68, and the value of the radius ratio lie within the limiting value of 0.414 to 0.732, hence the coordination number is 6. Rubidium occupy octahedral holes and iodide ion they form the CCP arrangement. And the limitations of radius ratio value. Radius ratio value in certain ionic compounds fail to predict the structure. For example, in case of silver iodide, when the radius ratio is calculated, it comes out to be 0.52. It lies within the limiting value of 0.414 to 0.732. So the coordination number is 6. But actually the coordination number is 4. And it has tetrahedral structure. Similarly, in case of cadmium sulfide, zinc oxide, the predicted coordination number on the basis of radius ratio value is 6, but actually the coordination number is 4 and the structure is tetrahedral. Number 2 limitation is that the coordination number 8 is predicted on the basis of radius ratio values for oxides of barium, strontium and lead, but no such compound is actually formed. Number 3 limitation is that radius ratio rule fails to explain that certain ionic compounds on crystallization adopt different structure with different coordination number. For example, thallium chloride crystallizes into forms having NaCl type structure, that is coordination number 6, and having cesium chloride type structure having coordination number 8. These variations help in prediction of actual structure for ionic solid because the anion do not act as hard spheres. Instead, they get polarized due to cations, which result in error with radius ratio rules are applied. Thank you.